Hello everyone. So today we'll be discussing problems on graph, basically on the algorithms, famous one, Dijkstra's, Prim's, Kruskal's, then they have Bridges problem, articulation point, then Kosaraju for counting the strongly connected components, then Bellman fault, okay, for getting the sorted distance, and then when there is a negative weights. Okay, so let's just start. So the first question is from the puzzles, half head. This is an interesting one, so definitely check it out. Next one is Dijkstra's shortest path. Okay, so what we are doing here is we are keeping a set of distance comma node, like basically there's a pair. Okay, think of it like a queue when we do BFS, but similar you can think of. It's not exactly the same, but yeah, a, a bit of same. Okay, so and also a minimum distance factor, since we have to return the shortest path distance from the source node to all the nodes, so we will keep a minimum distance factor. It lies with int max. Okay, and there is a set pair of this distance comma node. Okay, and we will be already processing the smallest kind distance, and that's why we're using set or priority queue. We can use that. So we are not going for queue because you will find it later. So we have the edges and number of edges, number of source node. We get prepare the adjacency list. We created the set minimum distance vector. We initialize the set with 0 0 because here 0 is the distance and 0 is the source node. Okay, task is to find the shortest path distance from the source node, and this is the node labeled as 0. Okay. All the problems our source node is 0. We have one input in the set. Now we are doing while set not equal to input. We get the top, we set a distance and the front from it. Okay, and we did that like that part, that value or instance, whatever they say. And then we did iteration for all the neighbors for it. Adjacency list of front. We got a neighbor, we got the weight. And we were checking like the distance, like distance of the front plus the weight is just less than the minimum distance of neighbor. Like think this part. This part is very important. Like this type of functions, FLs will be mostly used. So just think this part. Distance of weight is less than minimum distance of neighbor. Then simply update it and push this neighbor into the set. Pushing this neighbor into a set. Okay. And simply you got the minimum distance. So only two things are important. We are keeping a set, okay, and we are keeping the minimum distance factor. Rest of the part is simple. The way we do the BFS, sorry, breadth first search. We keep pushing into the queue and keep getting the front and traveling the neighbors. So this will feel a bit almost similar. So why we use set not like queue? Because we are interested in the like next shortest distance. So think this part. You will find it very interesting. Basically when we are using set, so okay, just think it through. This part is good. So Prim's MST. So what is MST? In MST, basically all the nodes are connected by certain edges and their sum of the weights are minimum. Let's just check it. If it's written, and MST for the graph is all the nodes are connected and their sum is also minimum weighted sum. Sum, not sum of all the weights. Okay, so first this will be going using Prim's algorithm, Prim's algo. So think like you are creating the MST from the zero node. Like we starting from the zero node. Where's the graph? Okay, we started from here. We are basically starting the MST tree. We are creating the tree from scratch, like from the zeroth node, then let's say one, then second, third, whatever we are creating, and adding the minimum weight at each time. Okay, first we add 0, then we go for 5, then we go for 8, then go for 15. Now we are adding the smallest one step by step. We will needing three vectors. One is the minimum distance, initialize with n comma int max. Initialize with int max. Then keeping a MST bool. So basically, this will tell us whether the node has been added to the tree or not. And there's a parent vector. Okay. And how we are going to do this? This is the same steps. Like we have to get the minimum of the weight and the node value, and we will set that node to be true. Like we have added that node to our MST tree, and we'll check for its neighbor and put it into the. We will update it min distance. Okay, updating min distance and parent. Great. So we got as adjacency list. We initialize our three vectors: minimum distance vector, parent vector, and MST vector. We set a minimum distance vector of 1 is 0 and parent of 1 is -1. Okay, we have to check that what is the variation of the problems. Okay, the sample input, there is no node starting from 0, it's starting from 1. Okay, so that's why we set dimension of 1 for, sorry, we set dimension distance of 1 is equal to 0 and the parent of 1 is equal to -1. Okay, and this is our main step. Like, we set the for loop for all our nodes. We want to get the minimum of the weight and the node, so we get the smallest minimum node, smallest, whatever we want to say. We traverse through all the nodes. We check that it must not be added to the MST, like it must not be a part of the tree, and the tree we are creating, the MST tree we are creating, it must not be a part of that, and the minimum distance should be less than mini. Sorry, if this is less than mini, then simply update it. Okay, getting the mini, and then we are separating the same u we got, same the node we got to 1, like we have added to the MST, and we are checking for its neighbors in this part. You have to think a bit, like spend some time thinking, you will find this good. Yeah, and we are keep updating the parents here. Parents we are updating because we want to connect the things. We are updating the parents, it will be difficult to create the tree. Okay, it is the same spanning tree but using the different method, using the Kruskal's method. Here what we are doing, okay, we won't be making adjacency list, we will be simply sorting the edges by the order of weights, and we will be using the like disjoint concept now. Like, we will make each nodes their own parents and they will keep adding them until you get a tree. Great. Now adjacency list, sort them by weights on edges, keep parents equal to node, root node. Okay, so you got a rank vector, and there is a concept of a union set. Great. Let's start by here. We will sort the weights on edges. We have sorted it. I defined a CMP comparator. What do you call it? Static bool comparator. Okay, CMP. We are comparing two vectors A and B, and we are checking only their weights. Okay. So if the we are sorting it ascending. Okay. If ART is less, then it's good. Then return is true. Great. It's also a function. Basically, this returns the parent of the node. Let's say what I mean by parent. There is no graph here. Okay. Let's just move. There's no interesting thing here. Planning tree, MST. Parent, you can think like going to the root node of the same part. Let's say if there is a leaf node in the left subtree, and you will move from there up until you would reach the root. So that will be its parent. Let's see that if node is equal to parent, return node. That's right. Parent of node is equal to find parent comma parent node. I think this part will find very interesting. It's good. And the rest of defining is union of nodes. Let's say there are two nodes, how we are merging them. So we are using the rank concept here. So the rank is different, how we are doing it. Like, u is greater than v, then what we're doing, v greater than u. It's exactly the same, but changing the variable uv. And if there's different, then what we are doing. Okay. So we are sorting them edges. We have parent vector. We have rank in size with 0. Okay. So starting with setting the nodes as their own parents. We got total weights is equal to 0. And then we are basically going for merging. We, let's say, for each of the wedges. Okay. Edges I0. Let's say this part 1. So we basically found the parent of 1 is u. We found the parent of this I equal 1 of 2, which will be, let's say, v. We got the weights is here 6. Okay, we will check that if both does not have the same root, like, okay, so we will be merging them. So we'll adding the total weights first, and this is the part of merging them actually, like, and this is the function of same I described above. This, so merging them, let's uv, we have the parent and we have the rank. Great. And these ones are like only formulated. We have to just, I think, follow the steps. In this part a bit and very difficult. So we need to create, we have to find bridges in the graph. What is bridge? Let's say bridge a point. If we remove this edge, so we will have two disconnected components. Okay, so like let's say there's one tightly connected components and you want to just remove, let's say we remove this edge to 0 to 2, and then still 0 1 2 will be connected, so we don't have any extra components. But if we remove this part, we'll have two components, 0 1 2 and 3 4 5. So yes, this is a bridge in a graph case, or you can solve simply this is a bridge. Okay, so how do we solve this problem? So we need few vectors. One is disk, low, there's a timer, a visitor, and we're using diffs. And there will be cases of package case, bridge case. Will keep a backtrack condition to update the low node. This is part a bit difficult here. Yeah, this is difficult. So we prepare the adjacency list first. We form a slice our four vectors of, okay, this vector, low vector, discovery time, lowest time to reach there. We have the parent, create a visited bool. So we started a timer and we are simply doing DFS. Okay. So just need to remember what are the different kind of data sets we need to initialize or use, and we are using DFS here. And this part is interesting. We started set the visit of node is true. Okay, send discovery time and low node of is equal to timer plus plus. Now we are checking for all the neighbors. If parent is equal to continue, these are the cases. Yeah, it will be difficult to just think it through in the first time you are solving the problem. So yeah, if you know, if you already solved this one, so it will be easier, because it's very difficult like to just think of these cases in the very first attempt. This is a package case. The low of node is equal to minimum flow of node and discovery time of the neighbor. Great. Maybe the DFS. We are checking the low of node is equal to minimum of low node or no neighbor. This is the backtracking part I was talking about. We check for bridge cases. If low of neighbor is greater than task of node. Okay, then simply update it in the result. Great. Spend some time into it. Yeah, this is difficult, really difficult. This is the articulation point. This is also when we remove the node and we have more components. Just see description. If you remove a vertex, and it just causes the graph to become disconnected. Then the vertex is called articulation point. Okay, I won't be discussing this because I have to check it again. This concept also a bit similar to last bridges one. Okay. Now things are getting a bit easier side. Okay, so counting the strongly connected components using the Kosa-Rajus algorithm. So what we're doing here, we'll do topological sort. We will using okay, we'll transpose of the graph. Next we'll be doing DFS. DFS, great. First we're doing topological sort, then we're doing topological sort. We will transpose of the graph, then we will be doing third step DFS. Great. Topological sort, get transpose, then do DFS. Only if you remember three things are easily solvable. Okay. So we get a adjacency list. We are getting topological sort here. We use the stack. We know that we are using stack for topological sort using DFS. So okay, topological sort. For sort we define the function. So this is our part. We are pushing into the stack here. Great. So now we get the transpose. Transpose from the adjacency list. We can say like we reverse UV. We did VU. Okay. The directed graph. Now we just change the direction of the edges. Great. After that, we did the DFS again and traverse the entire graph. So and we kept a count how many times we got the disconnected components. Okay. So yeah, that's the answer. Let's say here will be 2, 1, 2. Not disconnected components because it's a wrong term to use here. But let's say we started from 3 here. So let's say we have one edge 1. We get back again. Okay, that's for count strongly components. And then let's Bellman Ford. So it is similar to Dijkstra's, but here basically we can have negative weights. So it's this algorithm a bit simpler. Like for I minus 1 times we have to do this, and just simply checking like distance of u plus weight should be less than distance of v. The condition is true, simply update dimension of v. That's that simple. We have to do it for n minus 1 times, and we have to do one more time for nth time to check like if the distance vector, minimum distance vector is still updating, and it's updating, then there is presence of negative cycle. And what is negative cycle? Like simply add all the edges. If you find the negative like number, you will add it 5, 1, 6, 8, 9, 8. So it's not a negative cycle. No, it is if the graph is containing negative weight cycle, return -1. Has it defined what is negative weight cycle? Is it there? 9. No, it is also not negative cycle. Art. Okay, it contains the graph containing negative weight cycle formed by path. We started 1, 2, 3, 1. Okay, this part. Okay. This part is interesting. Okay, so what we have to do in Milnor-Ford, we have to go for -1 times. We have to check the condition. Okay, simply the weight of reaching there plus weight or minimum distance of u plus weight should be less than distance of v, and if it is there, we simply update the weight. We have to do it on -1 times, and we have to check it one more time again to check if there's negative cycle. Like if it's still updating, then there is negative cycle. Okay, these points are difficult, like all the famous algorithm. You have to almost remember them, because without like thinking them at the first time would be very difficult. Okay, then that's for it for today, and I'm getting bored in solving the problem, so I will move to contests. Okay, then meet you again. Bye bye.